acting here. If B suddenly disappeared, then you're saying that force would be gone and A would hover. So what happened to that? They come in pairs. What happened to that other part of the pair?
It took to the ground.
It suddenly gets transferred?
Yes.
No.
No.
Remember that the gravitational forces don't require contact. So there is indeed a force downwards here. This is the weight down there, but it is still up on the ground. But you have illustrated another rookie mistake. Weight is between the planet or moon and the small object. It is not between the two smaller objects yet. If you wanted to look at the gravitational force between these two objects, I will just let you know, one, it's insignificant, and two, it's a path to madness. And we want to avoid that.
Is it like just a bunch of fighting to get to nowhere?
Well, I mean, if you're going to look at the gravitational force between those two objects, well, why not the gravitational force between the top part of A and the bottom part of A?
Okay.
Why not the right side and the left side? Matter of fact, let's break it down to the atomic level and look at all those forces. We do not want to do that.
That's when the fun comes out and I go, Einstein.
And the only people who care about the gravitational forces between those two objects, besides when we get to those board problems, are people who actually study gravitational forces. I've done the rain in the hill explanation, right? I talked about that. There were some people who were doing gravitational studies and they noticed they got very different results in the spring than they did in the fall. And they were trying to figure out why that was. That because they were in the basement of the physics building, there's no reason why it should have been different because of the season. And eventually they figured out that in the spring when it rained more, water soaked into the hill. That was on the other side of the wall because they were in the basement on the other side of the wall, and that was throwing off their experiments. Those are the people who care.
Fair.
On my dissertation, I did not care. All right. Any other gravitational forces?
That was a yawn of no.
Yeah, what about B? Which way is the force acting on B? All right. Nothing needs to be erased, but there is a mistake on the board. Another rookie mistake.
Putting two arrows on the ground.
Nothing wrong with that. I got two objects being pulled down, but the objects are pulling up.
Yeah.
What is this force right here?
Wait.
From?
Gravity.
Okay,
On the ground.
You sure it's A?
well, we did it first, so I was about to say, we need to label.
Oh, we have to label.
When you have multiple of the same type force, if you do not put another label here, if you do not somehow differentiate them, you are making the claim that the weight of both objects is the same. And that is not an assumption you probably want to make. So we need to somehow differentiate them. Yes, this is the first one right here, that's the one I wrote down when I did A, but it's not guaranteed the way I've done it. I mean, if I handed this to you and said, hey, this weight is associated with which box, you wouldn't know. So, in terms of labeling, personally I like to label them so that they make some sense to the diagram, and I generally start at the top and work my way down. So I call this weight A, and then one of those on the bottom gets a subscript A, and then I put a little B here. Now some students will ignore those subscripts completely, and they'll have on the test problem that you're going to get for the second test, there might be 6 different objects, and they'll have 6 different weights, all labeled W with no differentiation between them at all. And I give them credit for the first one, and I take off for all the rest of them. So don't forget subscripts. All right, so weight is done. I have two objects. They both have force acting down. Again, there's no force acting up on B of any consequence. We're done there. Normal force.
Well, there's a whole smorgasbord of normal force right now.
Okay.
We have between A and B.
All right, which way is it acting on A?
Up.
That is not necessarily easy to see. And where's the other part of that curve?
B, which is down.
I give it the same label because those are paired. Those are going to be equal in magnitude, opposite in direction, acting on different objects, the way I wrote over there. So that's Y sub A. All right.
And then it's gonna be up on B and down on the ground.
Then that's the force diagram. Oh, you about to do another one?
No, I thought I'd made a rookie mistake, but we're good.
The most common rookie mistake I find here is people putting a normal force between A and the ground, ignoring the fact that contact is required. All right, questions before we actually apply this to something? Let's apply it. At this point, I assume all of this stuff is internalized, or at least written down. All right. So, let's do a force diagram for, I got a planet right here, I've got a scale, analog scale, and I got a person standing on the analog scale. Let's do a force diagram. So I got person, scale, and ground. All right, what's the force diagram look like? Justin, it looks like you want to say something.
Are you asking like that?
Yeah, it's gonna be like that.
Okay.
Yeah. The only difference is it's not a box or not box A and box B. So I'm gonna make my subscript just a little bit different, just again, trying to make it seem somewhat relevant to what's going on here. So I got weight, I'm gonna do P for person, WP. I got weight of scale, weight of scale. Let's see, I got normal force on person. Then there's normal force on scale. And that should be, so we got 3, 3, and 2, 3, 3, 2. All right. Questions about this force diagram over there? All right, so I step on a scale. What does it measure? No. 4. It does measure a force, yes. Looking for something more specific. Pardon?
Mass?
No. Balances measure mass, scales measure force. And the reason you know this will not, well, hopefully you can imagine, why this does not measure mass is that if I took this scale to the moon and stood on it, I would get a different value than on the Earth. So weight changes depending upon the location. All right, so first off, let's address the weight issue. I was hoping somebody would say it, so thank you for playing along. If I am not, so let's say the scale's over there, what would it read? Yeah, so it's not measuring my weight then, so why would it measure my weight if I move?
What? Because I stand. Move it up. Because I'm on it now.
All right, when you first step on the scale, analog scale, what does it do?
It starts going up. To give me a number of how much it was.
It goes just straight to that number?
I mean, it fluctuates a little bit. But
If I did that onto the scale, what would it do?
it would probably exceed a bit and then come back down.
So when it hits that maximum, 300 or 400 pounds, whatever it happens to be, does that mean I weigh 300 or 400 pounds at that moment?
At that moment, yes, sir.
Let me reword that. Does that mean that my weight is 300 or 400 pounds?
You grew substantially.
And then I have instant weight loss? There you go. There's the multi-million-dollar idea for weight loss. Just bounce on the scale. Yes, you gain a lot of weight, but you also lose it.
Okay, so if it doesn't measure your weight, does it measure your force with respect to something, or something with respect to something? I'm thinking.
All right, let's think about the diagram. Oh, Tristan.
Does tension be weight? I mean, on a scale, you measure tension?
Scales I don't think usually measure tension. I think it's a compression. The spring in there gets compressed as opposed to pulled. But the scale is reacting to me. If I stand on the scale, it's reacting to me somehow. It has to be based on some force I'm applying to the scale. What force am I applying to the scale?
Normal force.
What the scale actually measures is that. That is what it's measuring. That is why it goes way past what I need and then goes back underneath. If I'm bouncing on the scale, eventually it'll settle down if I settle down. It measures this normal force, which is equal in magnitude to that normal force. Let's connect it up with chapter 2. When I first step on the scale, I'm coming down onto it. So I have some speed downwards, or even a velocity downwards, and when I step on the scale, I come to a stop. So I'm slowing down. So when I first step on the scale, I slow down to a stop. Well, since I'm traveling in that direction, and I'm slowing down, the acceleration is upwards. If the acceleration is upwards, that means the net force is upwards. And this is the connection between what we did before and what we're doing now. So when I'm stepping on the scale, the upwards force is bigger than the downward force on me. So YP is greater than WP. And so the scale is going to read something greater than my actual weight. When I'm bouncing up and down, as I'm bouncing up, when I get near the peak, I'm traveling this way, but I'm slowing down because I have to stop to come back down again. So when I'm bouncing up and I'm reaching that peak, I'm going this way, I'm slowing down, so acceleration is that way. So therefore, in that situation, the weight is bigger than my normal force. And because the weight's bigger than my normal force, the normal force, obviously, less than my weight, so it's going to read something under my weight. I don't suddenly weigh 50 pounds. Or I don't have a weight of 50 pounds. So, a real life application of box on the ground. Ready for the next one? Carolyn, doesn't look like you're ready.
Yeah, I think I am.
Is it messing up your world to say that scales don't actually measure weight?
Maybe.
The reason why we say that it measures weight is that if I'm standing perfectly still on the scale, then I'm in equilibrium. If I'm perfectly still, my velocity is 0, acceleration is 0, my position is, doesn't matter. If my acceleration is 0, I'm in equilibrium. If I'm in equilibrium, then these two will be equal to each other in magnitude. So the normal force equals my weight. And since the scale measures my normal force, we say it's measuring my weight.
But in reality, like that is nigh impossible to do, to have equilibrium while you're on top of the scale.
Why?
Because there's no way you're gonna possibly be able to stand completely still. You're gonna move a little bit, you're gonna hesitate a little bit.
I thought you would go for it. Yes, I'll agree with that, but there are two other big things that also throw it off. One, buoyancy. I'm surrounded by a fluid, air. It holds me up a little bit. Also, the earth is spinning. And there's a video out there where I go through and I take both of those into account and talk about the difference between what the scale measures and your actual weight.
I'm not 10,000 pounds.
All right. Next installment. One that you will grow to love or hate because you will see it a lot.
Box on right. Dun, dun, dun.
Now, I've drawn it like this to indicate that the ramp is part of the ground. It's an earthen ramp if you need. I put a box on it. When you draw the force diagram here, I recommend drawing the box in the same orientation. Not everyone does it. Personally, I just find it a whole lot easier when you're drawing forces to not have to think back of, let's see, how was this oriented again? When I draw my arrows. All right, what can we get rid of?
Now, hold on. For clarification, I don't think we could get rid of friction this time
Correct.
because it's on an angle and it can very much slide.
Yep.
Thus, we would say that we would have the arrow pointing,
Oh, you want to do friction first?
yes,
Okay.
let's do arrow on box pointing downward.
So friction is up and down the ramp?
Yeah. No. Wait a second.
From the ramp's point of view, which way is the box gonna go?
It's down.
And the ramp says, not on my watch.
Not on my watch.
So the ramp wants to oppose that.
Opposite. So it'll go up.
But forces come in pairs.
Friction is going
Down the ramp. Be careful about if you say it's going down, down is that way. For the hand gesture, this is down the ramp. All right. I mean, you can even amaze your family. Thanksgiving's coming up. If you get together with your family, talk about physics the entire time. They'll love it.
like that.
Got a ramp, have what we'll call the box. As it slides down, I can see that it's causing my arm hair to go that way. That's this friction force that's doing it as it slides down. All right, friction, done. I have only two objects touching each other, so there's friction. Typically, friction is a good one to do last, but we dare to be different.
We don't have any tension. I don't think. Nor do we have any boogeyman force. We do have a no.
Yes, we do. which way is the normal force acting on the box?
It's, okay, now, my brain,
All right, before he processes it verbally, in your own minds, think about what it is. And then be prepared to go, Ibrahim, what were you thinking? And you can throw in some other things, like question his entire existence, things like that.
all four, let's go. So, if your normal force is opposing, so it would be opposite to the ramp. But if your normal force is this going that way,
That way?
yes, then my brain's thinking it's gonna fly.
Okay. Anybody wanna challenge his existence? All right, so basically we have two options here. One, it's a repulsive force, so the two arrows will be opposite each other. Well, they're all opposite, it'll be like that. Some orientation. So the question is the normal force up, or is the normal force at an angle? Let's ignoring the flying piece for right now. Up or at an angle? Rookie mistake is to always put it up. So yes, it is indeed that direction. And therefore, the other part of that pair? It did right. Okay. Tristan, you were about to ask a question? Okay. Anyone else with a question at this point before we do the last force, and then we'll address Ibrahim's flying issue? All right. Gravitational force?
Straight down.
Yeah. And the other part of that? On. Now, it doesn't have to be directly under that one, just anywhere on the ground is sufficient for this up arrow. All right, so those are done. Now, let's address the flying issue. There are three forces acting on it. We know from experience which way this box, if it's going to accelerate, which way the box